Okay, we're going to go ahead and get started since we've only got an hour with you all and we have a lot to talk about. I'm Chris Wilson. I'm with the U.S. Green Building Council, and thank you all for coming and for your interest and for providing the content as your presenter. CSHQA was kind enough to host, so there's not too much to know about this space, but if you want some water, go to the bathroom, just go past the reception desk, and there's a little break area, and the bathroom's right past there. Take a right. And the city has taken an interest in expanding the geothermal system, and they've got some innovative new ideas of how to do that. So John Gunnerson, the city's geothermal director, has come to tell us, give us an overview of the system, the history of it, and then where it's headed. And then we've got a case study in this building right here, which connected a few years ago. And Mike Jones is here to tell you about the mechanical system and how that extracts the heat from the geothermal water and heats the building. And then we'll do a little Q&A, forum, just open format, and me and Silac with Concordia have come, and they've connected their building. So there's another perspective of a building that's been connected recently. So it should be a good format, and we'll try to keep it on time so you can all get on with your day.
Okay, well, thank you. Again, I'm John Gunnerson. I work for the City of Boise. I'm the geothermal coordinator. I operate and maintain our geothermal system. It is the largest geothermal system in the nation. It's about the 5th largest in the world. With that said, we're heating right now 86 buildings, just under 5.5 million square feet. This is kind of a boilerplate presentation. I'm going to try to do some really technical stuff a little quicker. But at any time, feel free to interrupt me, stop me. Very important. So, as we all know, basically everybody's heard the term geothermal. There's really 3 classifications of geothermal. There's a high temperature, low temperature, and ground source. High temperature, usually above 350 degrees, used for power generation. There are 2 in the region are the Raft River Power Plant and the Neal Hot Springs in Eastern Oregon. Great option for electricity generation. I understand one of the biggest concerns is the delta T. When you need the peak loads in the summertime, geothermal power plants don't work as well in the summertime. They work better in the wintertime because you have to have that delta T. The coefficient of performance is much higher in the wintertime. The other end of the spectrum, ground source heat pump, we all know about, using those constant temperature, heating and cooling. And what we'll be talking about mainly today is that middle tier, low temperature geothermal. We pump our water out at 177 degrees Fahrenheit. District heating is not a new concept in everybody. It goes way back. A lot of bigger cities had power plants downtown. They take that waste heat from power plants, pipe it to downtown. They use that waste heat to heat buildings, to heat water, to other uses. What's unique about ours is our water is heated naturally, and that's the only difference from those other heating districts. Heating water naturally isn't something that anybody can do. We are very fortunate to have it here in Boise, Idaho, and such a close proximity to the downtown core. There is geothermal potential in the central mountains, but there's really no population base to develop it. Then I'll go through the history real quick. So along the Boise front, historically there used to be a handful of artesian hot springs. For centuries, this is where Native Americans would come in winter, and there would even be no area of truce. If the different tribes were battling and fighting, they would come to these hot springs, and no more fighting going on. When Boise was starting to be developed, I think the city was platted in 1863. About 30 years later, we saw the potential for its use as hot water. Right where one of the hot springs was bubbling out of the ground, they put a well there and drilled right down on top of it, and captured the first geothermal water, and is really attributed to Boise's growth. In the next 100 years, many people are familiar with the natatorium. It was a very prestigious, grand structure that was in East Boise. It burned down and blew down back in, I want to say, the 40s, 50s. All the houses up and down Warm Springs Avenue are still heated with geothermal water. There's a lot of history going of how that system is it's today referred to as Boise Warm Springs Water District, but it goes through a whole iteration of different companies owning it, from Boise Artesian Hot and Cold Water Company, splitting apart, selling it to Natatorium Water, various things. So, bringing it to today, there's really 4 geothermal heating districts in downtown Boise. The city of Boise is again the largest. It's this one shown in pink. The historic one, built in the 1890s, is the green one. Their well houses are right over by the old state penitentiary. And then there's 2 other really small districts. The state of Idaho has a small district. We have the only state capital that's heated by geothermal water, and the whole Capitol Mall is heated with geothermal water. And the VA also has a small one. The difference, all these systems are using the geothermal water primarily for space heating. These 3 though, the VA, the state, and mine, it's a supply injection system. Everywhere you see a line on our system, it's actually 2 lines. A supply line taking hot water to a building, the heat's extracted out of the water, then we collect the water in through another set of pipeline and take it to an injection well. We re-inject every gallon that we pump out. The historic Boise Warm Springs Water District, they are a distribution system only. They pump the water out of the ground, they take it to your house. As a homeowner, it's your responsibility to figure out how to dispose of it.
So it's pressurized, or what, right?
It is pressurized as well. Yep.
It goes into a lot further to downtown than like the mansion.
Yeah, we have a cross connection right here at First and Idaho, First and Idaho. And so right now, I can provide them water. They run at a very low pressure. We run at a much higher pressure, so I can give them water. So if they ever have a need for it, if their wells are down, if their system's down, they can isolate portions of it, we can supply them. It doesn't work the other way right now. We are considering perhaps a booster pump so that we can share water both ways. We also do have an interconnection with the state of Idaho. So when they redid the Capitol, because it's a state building, they had to either put in a backup heating system or some kind of redundant heating system. And so their option was our redundant heating system is another geothermal system. They'll have their geothermal system, but they're not going to redundant system using our geothermal system.
John, are all 3 systems the same temp coming out of the ground?
More or less. All the wells, I'll get into the geology here in just a second, but what's really unique is Boise Warm Springs wells, our wells, and the VA wells. You can literally draw a straight line and connect them all, and that's not a coincidence. There's a fault line that runs right here, and so water takes the path of least resistance. So historically, this is the line that Artesian Springs were coming out. And so we can actually tap into the water. Our wells are about 400 to 600 feet deep. In contrast, our injection well is 3,600 feet deep. The aquifer is really 3,600 feet down. It's just that it takes its fault line. So it's next slide.
Real quickly, are all of the wells accepting new connections, or have they shut any of them down for the next?
Currently, there's a moratorium on the geothermal system, on the geothermal aquifer. There will be no new development of it right now.
No new wells or no new connections to existing wells?
No new wells.
So then,
Another district can't come to Boise and say we're gonna start our own geothermal district and try to start connecting buildings.
but all of the ones that exist can continue to grow.
Within their allocated water rates. And all touching on that here. So again, our system is a 2-pipe system, supply line, collection line. Our supply line is typically insulated everywhere it goes, try to maintain the heat as much as we can, even to the buildings. We're pumping out the water at 177 degrees. We tell businesses that you'll probably receive it about 160, 165. At times it's much hotter than that. Then we advise, we set our rates based on taking 50 degrees of heat off this water. And if you take 50 degrees of heat off this water, this is a cheaper heating source than natural gas. Currently, natural gas is our cheapest heating source, so we set our rates to be below that. Historically, the city shadowed natural gas and carried a 30% differential. but in the last decade, natural gas prices have just been plummeting, and it's been really hard for us to compete. So right now, we're somewhere in the ballpark of probably about 5% savings from natural gas. It really depends on how much you use and what times of the year you're using it on different tiers of natural gas. I'll break our system into really 4 areas real quick. There's the collection system, utilization, piping, and disposal. We kind of just hit on the piping system.
Sorry, can you go back to rate? The rate is set on 50 degrees of heat out of that water. So are you charging per gallon or?
Okay, so we charge per gallon, and I'll touch why in a minute, but really what's going on is we're limited on how much water we can pump out of the ground.
Okay.
So I can't let these buildings just pump as much water as they want, or use as much water as they want, and only take out small amounts of heat. So it doesn't make sense to build them on a P2 or per therm. So we build them on the gallon, and so you charge 1 gallon, and then we make the assumption or the recommendation you take 50 degrees of heat out of that. And so you can quickly turn that into renewable energy. A BTU is the amount of energy to raise 1 gallon of water for 1 degree Fahrenheit. We have 1 degree of water and we take 50 degrees heat out of it. I believe it's 407 BTUs per gallon of water.
Of heat that's given out?
Of heat that you're taking out of the water.
If you take 50 degrees out of it, or just for every degree?
If you take 50 degrees of heat out of it, it's 407 BTUs per
Or
gallon.
is it?
Yes. Now, it works both ways. So we don't police, we don't monitor how much heat the building's taking out. So if this building we're sitting in decides they only want to get 30, 40 degrees of heat out, that's fine. But it's probably not the most cost efficient way to heat the space. On the flip side, if you got a heat exchanger, you got the controls that you get 60, 70, 80 degrees of heat out of it, your savings is exponential compared to the next cheapest heating source. Utilization system, there's a handful of different heat exchangers on our system. The most common is the paint frame heat exchanger. Essentially, you got the building water running one way, and you've got our geothermal water running the other way, and based on the size of your building, it determines how many plates and what kind of heat exchange you need. Uses of our system, the primary use is space heating. After that, the next highest use is domestic water heating. But we also have 3 systems now that use it for sidewalk snow melt around the facility. The latest one is the Uwali Plaza. That's the picture of the Uwali Plaza building right here. And then a handful of just odd and end uses. The YMCA heats their hot tubs, their pools. Elks Hospital heats their therapy pools. The Hampton Inn heats their laundry facilities. There's a kind of aquaculture, where they play with different fish and different aquatic life over on the Warm Springs Avenue. It's not my water, but just another use of geothermal water. There currently aren't any on our system, but there's Edwards Greenhouse in Boise. There's the turbine greenhouses. There's many uses for this water.
I have a question for you. You talked about the pricing, being competitive with other energy sources. Does the district measure, how much it costs? I'm assuming it's just maintenance of the system and pumps that are the core costs. Are they, profitable, or is it a break even? Is it a...
It's a break even for our system. We're definitely not making money at the end of the year, and it's a good year about not losing money. It's really just the cost of business. Although this is the city of Boise, this is not subsidized. There are no tax funds going into this. The entire system is ran off of user fees. So it's we do everything we can. It's just natural gas has really been hurting the system over the last decade. But last October was one of the first increases we've seen in 7 years. So we're hoping to start running that differential. We're hoping to keep our rates the same. Natural gas starts climbing and building differential, and it's just more of an incentive, more appealing to connect on
So you're not PVC, sorry. You're not public utility.
We are not part of PVC.
On the green line, you said it's up to them to dispose of the hot water. How do most of them do that?
Most of the houses south of Warm Springs Avenue dispose into the Boise City Canal. Boise City Canal, if you go right by the natatorium or the water treatment plant over there, you can see the canal there, and it's really, really fascinating. You go there in January or February, and the whole canal is steaming. There's big elephant ears and bamboo and all these tropical plants growing on it. It's really good. Where it kind of creates this artificial microclimate there. And then in the summertime, there's irrigation water coming through, so you'll see a difference. On the north side of the road, most of these places are disposing into the city's sanitary sewer system. That creates its own set of issues that we're trying to deal with. And now with temperature being considered with EPA, we're having to deal with temperature down at the treatment end of it. And so we're really seeing, is this really making a big impact? And in the summertime, heat's not being taken out of this. And so a lot of times 177-degree water is being entered directly into our sewer. And odors up and down Warm Springs Avenue become an issue. All of our manholes have to be sealed. We just got done with a huge rehab project to reduce some of the sewer, the alignments, and try to prevent any hydraulic jumps or anywhere that sewer gas is being picked up. And then there's probably a dozen or 2 dozen homes that have their own infiltration facilities, some kind of seepage bed or shallow injection well. They have somewhere around 300, 350 homes connected to their system.
If they're not pulling any heat off it in the summer, why are they disposing?
Well, only a handful of them are built by the gallon. Turns out the way Warm Springs Water District does their building is by the orifice size. So you buy a house on Warm Springs Avenue for $100 a month. Here's your orifice. As much water as you can get through there, you can have it any time of the year. And a lot of these houses don't have control valves. So this water is flowing into the building. Sometimes it'll go to the heat exchangers, sometimes it'll just bypass the heat exchanger and go to disposal. Some of the older homes, you drive down Warm Springs Avenue and you'll see upstairs the windows are open in the middle of the summer. And it turns out that they would put their radiators right underneath their windows, so water would flow through these radiators year round. And in the summertime, or in the wintertime, your windows are closed, you start heating the space. In the summertime, you open the window and it just exhausts right out there. You would think a control valve would be a pretty simple fix, but they have the rights. They've been doing this for 130 years, and some of these houses have made improvements. Some of them are still going off older systems. Chris?
The questions have been great. I would just ask that we focus a little more on where the system is headed rather than the history at this point, just in the interest of fitting everybody's presentations in.
Buildings that we, again, we're heating 86 buildings, some of the biggest buildings downtown, so we're in today, across the street. We've recently gone over to Boise State. We're now heating 9 buildings over at Boise State, with land and water and pipeline. We're starting different incentives to try to sell and promote and kind of get the word out about geothermal. There's so many people who live here that don't know about it. There's so many people that visit Boise that don't know about it. So the city's taken all kinds of stances to make this more, turn into a public campaign. Most recently, about 5 years ago, we started providing these plaques to buildings that use geothermal as its primary heat source. So the next time you walk through downtown, you'll start seeing these. So a lot of buildings. And then the disposal system, and I'll go through this really quick too. Historically, when the system was first built, we did not have an injection well. When it was first built, we discharged to the Boise River. And it didn't take very long to realize we were having problems. What we're looking at here is a hydrograph of the geothermal aquifer. We started pumping water during 1983, and I mean there's seasonal variations, but you can see after the first year it didn't rebound as high. After the second year it didn't rebound as high, and we were really harming this resource. And so the city called timeout. We found location funding. We did geoseismic surveying all through downtown Boise, trying to find the right location. Finally, here in Julia Davis Park in 1999, we decided to drill an injection well. It's an over $1 million endeavor for this well. And then, let's see, so here in 1983 is when we started our system. Then here in 1999, we started operation of the injection well. And you can see the very next year it started coming up. The very next year it started coming up. In 2006, we ceased all discharge to the river. There was still a handful of buildings that it was really tough to get them back to the injection well, so we kept them going to the river for 7 years. But there in 2006, we stopped all flow to the river. And the high point continues to grow year after year. And we're actually seeing those comparable to when we started pumping. And so this is a true success story of how the city has managed the system. We saw the problem, we took steps, and found a solution. Pumping limits. So because of that problem we have with the aquifer, Department of Water Resources stepped in. They put this moratorium on the geothermal aquifer, not anybody else who develop or drill into it. We currently do not have a water rate for it. We're under this stipulated agreement with the other districts of how much water we can use, and we get increases every year. Proven, there's no additional harm to the aquifer. So we monitor it continuously for level, for temperature, for pressure, and we all get together once a year, and as soon as there's no problems with it, we ask for our increase, and we're getting on average about 10 million gallons of additional water per year. Just a quick note, this was the low point here this winter. We had a very mild winter, so you can see kind of what that impact had. As I was expecting, what we've seen for the last 3 years is, yeah, the high point's gotten higher, but the low point has also been getting a little bit lower. And it's really the low point is what we're concerned about. This last year, really, it's a mild winter, but, we're hoping that trends keep going up. Here's just kind of an estimate. This is what I'm looking at on a weekly basis, how much water we're pumping. It's just kind of a standard bell curve. And most of our use is in December, January, February, but we still have quite a bit of use year-round through the winter. Really quick, EROI, energy return on energy invested. It's a hot topic I'm hearing more and more about. Basically, it's the principle of how much money do you put into a system, how much energy do you put into a system, and how much do you get out of it. Some of the highest are hydroelectric. It costs a lot of money to build a dam, but that dam's going to continue to produce electricity or produce energy for its design life. You really don't put any more money into it. Well, same thing, I guess another great example is the biodiesel. It is a huge, or the corn diesel, is a huge idea and a huge philosophy 10 years ago. They quickly found out that the amount of energy it takes to plant corn, to irrigate the corn, to harvest it, to process it, to refine it, you're really putting in 1.5 gallons of gas to get a gallon of gas out of it, and it had a negative EROI. Maintenance and repairs on our system. This is my biggest obstacle is corrosion on the system. Boise is just notorious for very corrosive soils. And with the accelerated temperature, it makes fittings fail really quick. Some of these fittings we're seeing are failing in less than 2 years. And so that's the forefront of what we're doing every day is cathodic protection. How can we prevent this corrosion? And the most obvious and most successful is let's just keep metal out of the system. Here's some pieces of pipe that we're using. Everything we're using now is fiberglass. All the fittings, all the couplings, all the T's, all the taps, everything's fiberglass. What we can't get away from is some of the valving. But where in the limited areas where there is metal and we have to maintain it, we'll strap anode bags to it. We will put them in vaults to remove the soil metal interface. It's as simple as going down to the Napa Auto Parts and there's some undercoat spray that you put on the underside of your car that really prevents corrosion from the salts in the winter. we take all three levels of these every time we go on the ground. Last thing we want to do is come back in 2 or 5 years and replace these.
In those fitting areas where you have to use something other than fiberglass, are they in a manhole or something accessible, you don't have to actually dig the pipe back out each time?
Not always. A lot of time the volume manholes just to remove that soil metal interface. If we have to replace it or repair on it, we'll probably still be digging there. It's just so we're not backfilling right up against these metal fittings.
Follow-up, is the Broad Street streetscape redesign and construction project a potential innovation lab to where you could test out a vaulted system for places you know would fail more regularly?
Perhaps, yeah. Well, we have been working with the manufacturer of these tapping saddles is a company known as Romac. And so Romac has been providing different samples for us to put in the system. They want to get on the forefront of this too. I mean, it's their industry to put tapping saddles and put different fittings together. And so when we approach them with our drone, they want to get involved. So they're sending us samples, we're working together. We've got some of their samples buried. We're digging some of these up, we're sending them to them. Another huge help has been the Boise State University's Material Science Department. I give Mike Hurley their call a lot of times when when we have a break and we're out fixing it. And just about 2 years ago, Mike Hurley published this failure analysis report of these stainless steel tapping saddles. And I don't know, there's a lot of emphasis, there's a lot of eyes on corrosion, because that's really the hardest part of this system and a lot of pipeline systems. Okay, so kind of getting into what we're doing new. This is an incredible technology that we've now been doing for 2 years. Basically, there's this guy locally who he flies over the city and he'll look at buildings, and he'll look at the heat signatures of those buildings, figures out where the inefficiencies are. And he gave me a call, and it took him the longest time to figure out what are these lines doing out in the street. And once we connected, we looked at our maps and realized that these are our geothermal lines. And we can see them with this aerial photos, with these infrared photos. Not only can we see them, we can see, like over here, we can see leaks, we can see hot spots. So we've always been a very reactive system. We wait till water starts bubbling up, then we start digging down and trying to figure out where's it leaking, what's it doing. These last 2 years, we've been digging on dry pavement, which is just unique for our construction crews. We've never had this proactive approach. So we've done this for 2 winters now. And this is last winter, we got the entire downtown floor, and then we stitched all these pictures together, and pointing out the Boise City Canal, going in the middle of the winter. There's no irrigation water, all that heat is coming from geothermal. And there's a lot of detail in here. There's a lot of really good things that we found here. We actually, because of the success of the reinjection, how the aquifer level came back up, we're beginning to see hot springs come back. And so we recently just found one in Castle Rock Park. There's kind of a wetlands there, and we're like, what's this hot spot doing over there? And we go over there, and sure enough, it's bubbling out of the ground. And we were warned that that might be a problem with this reinjection. I mean, what side of the fence do you want to be on? We don't want to harm the aquifer, but yet they say if we reinject, we might be causing these other problems. This is the only one we've seen surface, but the Warm Springs Water District well houses are artesian, which they haven't been in 30, 40 years. We're seeing more artesian pressure on our wells than we've ever seen. So the pressures are increasing, and it's really contributed to a lot of the success of the reinjection.
And the death of house.
Yeah, yes. Well, yeah, so I mean, there was that dog incident, and we were doing sewer work on Warm Springs Avenue, and there was Warm Springs geothermal line right next to us, and our contractor said, this is a hazard. We've got to work down here in the trench. If something ever happened to this geo line, we're going to be cooked. So, is there any way you could turn this line off? And Warm Springs Water District said, yeah, of course. They understand safety and water front. So they turned it off, but they didn't realize how much artesian pressure these wells still had. So they turned it off, but this water still had to go somewhere. They did not have one of the valves at their discharge tank. So what they had to do is they had to disconnect their pump from their distribution system. They just turned their pump into the nearby canal. Get it out of the pipeline, put it somewhere else. And this water's flowing, they have no way to turn it off. And so it went into a canal, and unfortunately right there by their well house is also the trailheads to the main stems of the trail. I know my dog, whenever he sees water running straight for it, you can't really stop it. So a lot of what Chris has been poking at is what we're going to be doing here, what we're calling the central addition. Let me go back actually, go fast. So pumping units. We were set, because of the problems in this aquifer, we were getting these pumping limits, and we moved all the other parties to understand our pumping limits. Right now, this year, I can pump up to 290 million gallons. But now, we talked about what a mild winter was, but even so, I'm still on the path. I'm projecting I'm going to pump about 270 million gallons. If it was a cold winter, I'd be right up my limit. In fact, if I project I'm going to go over my limit, I have the ability, we have an agreement with all of Boise State that they can be, that they're an interruptible customer. We can turn their water off at any time, and they have a backup heat for all the buildings. So we have these pumping limits. But we're about max.
Are there any feedback signals from your injection wells to your pumps that you just always pumping at a set level, or is it pumping on demand?
It's pumping on demand. So we maintain pressure in our system, and so we've got a VFD on our production well and our injection well, and so we're always maintaining the pressure. And so we maintain a higher pressure in our supply line, a lower pressure in our collection line, and so it's a system that kind of drives itself. As a customer, as a property, you get the water from our supply line at a higher pressure, comes into the building, goes through your heat exchanger, through any controls, and then back out to the street to our collection line without the need of a pump, without the need of you putting any more energy into it. It's a system that runs itself. But we're always maintaining our supply line about 60, 65 PSI, and our collection line about 30 PSI. And did that answer your question? So we're getting really close to our pumping limit. Again, we do get increases every year, but this only goes for another 2 years. In 2017, once we reach 310 million gallons, that's when this agreement expires. That's when we're done. That's when we can prove up on our water right at 310. So we're also in process now, working with our water rights attorneys to find the next steps. How are we going to get above this 310? And what water rights should we be applying for? We're talking to the other districts, trying to figure out what kind of agreements, what can we do? Because everybody understands the benefit of the geothermal, but right now we're in this tight spot of we don't have a lot of growth or potential capacity with our pumping limits. And so until we get that worked out, there's a lot of growth and development planned for right in this area. What I'm showing you here is what we're referring to as the central addition. And so this is a new redevelopment that the city's pushing for. It was coined at one point an eco district, a live district. It's where they're promoting sustainable building design, highly energy efficient, different stormwater management, alternative energy sources. The area is kind of bounded by Front Street, Myrtle Street, Capitol on one side, and they say it goes all the way to Broadway on the other side. And that's what they're coining as this central addition. Now, there's about a half dozen properties in here that have expressed interest in geothermal. And so when the time we were planning on this redevelopment, they approached me and said, John, is there any way we can keep this entire area with geothermal? And well, I'd love to, but I just don't have the water to sell right now. And so I can't commit to selling this big area. So what we're deciding, what we're doing is we're going to push this as a collection line district. I'm taking all my water to my injection well, and when I'm re-injecting it, the temperature is somewhere between 110, 120 degrees. There's still a lot of potential in that water. And so why not use some of that heat before we re-inject it? It's on its way, so right before it gets in the injection well, take a couple more degrees out of it. The biggest hurdle is getting people past what temperature it is. You know, some people say it's 110, 120 degree water. I don't want that. I want 170 degree water, which makes sense. But it gets down to the philosophy of don't get hung up on the temperature of the water. Just know that your building can be designed to accept the temperature of water. For example, College of Southern Idaho in Twin Falls is all heated with geothermal, or most of it's heated with geothermal. But their water comes out of the ground at 110 degrees. I said, when you're asking about temperature, there is the one exception, is the state of Idaho system. Their water comes out at 150 degrees. So it's slightly cooler. So they size their buildings and their heat exchangers and their pumps to handle different temperature water. So that's kind of been the biggest hurdle, is getting developers past the concept that it is a lower temperature water, but it's still a good heating source. One catch is you're not going to have those differential pressures. You're going to be coming off this collection line and going back to the collection line. So you will have to put a pump inside your building to get the water back to me. Here, actually, let me just pull up this map here. So basically what we're doing is we're going to tie onto capital here. This is one of our main lines. It's a really large diameter. Tap onto it here, come into the central addition, and then south into the injection well. This line's already existing, so turn that one, this one, and then I'm going to turn this line off. So our current line of the injection well is going to go away. So all of the used water over the entire city will funnel right into the central addition. And so we'll have lots of capacity, we'll have lots of water. Plus, being the lower temperature water, I really didn't get into the different uses. I think most people here understand the forced air versus heat pump systems. You really can't use the cooler water for forced air systems. So it has to be heat pump technology.
Or just a radiant floor.
Perhaps.
How much heat do they take out of the lower temperature? If you're taking it out of 110, what do they put it back in at?
20 to 30 degrees. Scott, what did we look at? Was it 30 degrees you're doing the fidelity?
33, yeah.
33 fidelity. It's a lower delta T they're taking out of it, but our rates for the collection water are half as much too. So there's that incentive of having cheaper rates, but knowing that you're going to have to use a little bit more volume of water, it comes pretty close to a wash. So because it's close to a wash, we understand that development here, they're going to have to have larger heat exchangers. They're going to need this little pump, probably a little bit bigger piping because now they have to push more volume of water through the building. So the city is offering incentives to connect onto the geothermal. And currently the incentive is the difference of cost from that you would pay for tying the supply line versus the collection line. That whatever difference that is, whatever increased cost your heat exchanger and piping is, we will subsidize that with 150% of geothermal water. So if that didn't make sense, if it costs $10,000 more for a larger heat exchanger, larger piping, we'll give you $15,000 worth of free water if you want to connect on the geothermal system. So there's already enough incentives to use geothermal, but here's one more to kind of offset that capital cost. Because that's the hard part with development, is if it's a developer, a lot of times he's building it to turn it over. And he doesn't care about the long-term costs. So it's a lot cheaper to put in a rooftop unit or a traditional HVAC unit. So here's an incentive to income. So there's no additional cost to the developer, and then there's still all these long-term savings.
You think they're gonna expand that to the rest of the city? Or do you have any customers taking supply or return water?
We do. I've got about 4 or 5 customers right now that use collection water. And right now, they're kind of the hardest customers on our system to keep going. Because unfortunately, well, let me step back. In the last 5 years, we've really been looping the system. We've been adding loops wherever we can. It helps with our hydraulics, it helps with our redundancy. But prior to 5 years ago, it was a very branchy system. And so if you don't have enough upstream users creating collection water, then there's not enough for them to use. So all of a sudden, we've got this building wanting to use collection water, not enough upstream users. So we have to artificially bypass water, called crossover. We're putting hot water into our collection line. And it turns out I'm bypassing more water than I would ever be selling if this customer is leaving a supply customer at first. I'm wasting this water just to keep the collection line warm. So it does not make any sense to put collection customers on this end of the system because there's just not enough demand upstream. It also doesn't make sense at the end of any leg. But this central addition is perfect because it's right in the center. I'm going to push all the collection water right through this area, and so it's an ideal spot for collection customers. But no, if you want to put one out here or over here, we would deny it because I don't want to waste 2-3 million gallons of water just to keep this line warm for collection building.
Do you just have, there's one injection well in Julia Davis, is there one at that leg that off the
There's
west
not.
end?
That's where we go to the Boise River.
And so that dead end spur that's a little north of there is just a dead end leg?
These?
No, just north, up, yep,
There you go, up higher,
heading west.
a little higher.
Oh, yes. This used to be, we used to serve Steiner's Laundry over here. There's nobody connected past that point. This is Idaho Power. Idaho Power is back on. They're using geothermal for primary heating. But see, right here is Plaza 121. Plaza 121 uses collection water. For 2 years, Idaho Power decided they didn't want to use geothermal. So the biggest user was off. I only had 2 buildings upstream from them creating collection water. And it was never hot enough for them. They just never had enough collection water. So all the way here at the extreme end, we had crossover. And I was pushing on average about 1.5 million gallons per month through there just to keep the collection water warm. I was wasting more water here, more revenue. I mean, if you put a cost per gallon than I ever see from the actual customer. So it was a bad business model. It was a bad idea. But this area is just, it's prime for it.
What about extending the service to the area south of Mount there, some developments that planned on River Street?
So this map's a little dated. We do have lines down to Myrtle, so this hasn't been constructed. We are going to be serving Jump. That's already completed. And so yeah, this line will create another loop, and we'll
So it'll branch out to the east then?
come across this way.
Yeah.
Well, I mean, here's River Street. We've got the whole potential to infill. But there's going to be a little bit of a lag. I mean, until we get this water right issue worked out. I mean, I'm close to my pumping limit. I get 10 million gallons additional per year. So that's on average 1 or 2, maybe 3 new buildings per year. So it's a good growth, but I mean, I've got a list of a dozen properties that want to connect. And so we're really deciding how to prioritize. I mean, right now it's on a first come, first served basis. ESU has 10 in their queue that they're asking me if they can connect, and I don't have the water for you right now. And so we've sold our water through 2017, knowing when we anticipate getting our increases, when will this building be ready to use water. For example, right now I'm running a service line to the Boise State Alumni Center. I really don't have the water for them this year, but I will next year. And so I'm taking these commitments, and so it's a tough game. And that's why we're really excited about the central addition, because we can add all this additional square footage to our system. We can offset that energy with geothermal, but I'm not gonna pump a single gallon more out of the aquifer. And yet we still keep all this additional space.
Okay, I'm just gonna do a time check. Mike said he's got 15 minutes of content, and we're bumping up on a quarter past the hour.
I just have one quick question, I know there's a lot of questions and not a lot of time, but, so if we're looking at that graph that you just went past, the geothermal, if we're taking another 30 degrees or 20 degrees, if we're injecting it at 80 or 70 degrees, is that gonna backfire in terms of the temperature that we're finding in the aquifer? I mean, because historically you just discharged to the river and you were using the resource.
So you're asking if we start injecting ice
That was
cubes,
just
are
level.
we gonna see the entire reservoir start cooling down?
No, yeah, no, never mind, I thought that was the temperature, but it's.
It's aquifer level you're measuring,
Yeah.
right?
I mean, you're hitting on a concern that is valid. All of a sudden, if we start re-injecting colder water, what's gonna happen to the colder resource? The amount of heat that we're gonna be taking out of it is gonna be pretty minuscule. We're talking about that these have to be heat pump buildings in this area. So, let me bounce forward. So, monitoring different buildings. This is a conventional forced air system. This is kind of how I look at a monthly to build. So we trend them over the month, how many gallons they use or how many million gallons they use. But then also per heating degree, how cold is it outside, how many million gallons do they use. With a heat pump building, almost as soon as it starts getting cold, they start using water. Okay. Here's a heat pump building. This is the Eagle Center. And so, heat pumps can move the heat around their spaces and be much more efficient with it. Well, as soon as it starts getting cold, they're not using geothermal water yet. It has to be much colder before we start using that water. So everything here in the central addition, they're not going to be using any water in the shoulder seasons. And when they actually do start using water, we're pumping thousands and thousands of gallons a minute. And what they're going to be taking off is going to be a couple gallons per minute in lowering that temperature. If you look at the mass flow, if you look at the Q in, Q out, it's so insignificant. I don't think it's a problem. Consultants, they don't think it's going to be an issue, but it's something we're going to be watching and on.
I was thinking if you got the temperature low enough, then obviously that the demand is in the winter, but if you got it cold enough in the summer, then you can heat pump that cold water and inject into that. But it just seems like with the seasons that, and with the situation, that's just minuscule.
It'll be interesting to see too how that, as your heating degree days drop, as historically looking ahead over the next 100 years, even climate change, as those heating degree days drop, what that will do to your system in terms of the resiliency of it, in terms of how it's sustainable for cost-wise, and whether or not you're going to hit this sort of inflection point when it loses its value because there's fewer and fewer heating degree days.
Perhaps, yeah. I mean, everything we're doing is relatively new. I mean, this system's been in operation for 35 years, and just in the 5 years that I've been in it, we've gone leaps and bounds of where it was. And I can't even imagine what we're going to do in 5 years down the road. Understanding some of these trends. For time, this will kind of be the segue for Scott. Here is Second Broad. This is the CSHQA building here. They've been connected for just about 2 years now. And so we're beginning to see their trend. And we're beginning to see, and you can tell me how cold is it going to be outside. I can pretty much get closer to being able to tell you how many gallons they'll use that month. Some of these other trends are oversized. Questions?
So what are the challenges if the city were to want to do an efficiency program to give them, try to give you more water, because of the 50-degree delta T, maybe that could be 70-degree delta T.
We've been kicking this around ever since you called me a year or two ago. And I mean, it's a two-edged sword. It'd be great to get the buildings more efficient, so then we have that reserve of water to sell to somebody else, to a new building, connect a new building. But as soon as you make these buildings more efficient, you just slash my revenue. And so when you make these buildings more efficient, I'm not getting as much water. Plus, if you make this, we'll say this building, twice as efficient, I'm not gonna be comfortable selling that water next year. I mean, we're gonna need some kind of trend. I'm gonna wanna make sure this building is that efficient for 3, 4, 5 years. And then knowing it's got a new trend, then I can sell that surplus water to somebody else. So what you're talking would really cut my bottom line way down in anticipation that I can sell this water to somebody else. But if you only bring this building down normally efficient for 1 year, and I sell this water to somebody else, what happens when they pop back up to not being as efficient? Now I've overcommitted my water. So it's a really fine line. I would love to see buildings be more efficient. Boise State is incredible. They're pulling 70, 80, sometimes 100 degrees of heat out of the water. And, I bother. And I think the difference over there is they have resources. They have engineers that's their entire job, is to trend and understand the energy consumption of these different buildings versus the courthouse or buildings downtown. They might be subbed out to a property management company. They're not watching as close as they could or should.
Just, Selena might have some issues with what that last statement.
Well, I just want to add to that, like, one of the intents of an eco-district is that the property owners work together to manage the district, and energy would be a component of that. So you use BSU as an example where they have dedicated resources to their building portfolios to make sure they're efficient. That's the direction that we'd like the central addition to move. So I just want to plant that idea since you pointed out really well, BSU.
Thanks, John.
Yeah, thank you very much.
So before I get started, is this building on supply or collection water?
Supply.
Supply. So I don't know how he memorizes that for every single building downtown, but he does. So anyway, my name is Mike Jones. I work for SEED Idaho. I'm a mechanical engineer by trade. Our company offers commissioning and energy-related services. I was the commissioning agent on this job, which is why I'm here. Russ was actually the designer at CSHQA. He designed the building. If anyone knows it as well as he does, I do, because I've been through it with a fine-tooth comb. Just jumping in here because I have 7 minutes. There was an integrated design philosophy here. As one thing to point out that the architects and engineers really hit the head on is that just because we have such a valuable resource doesn't mean we should waste it, right? So architecture, actually energy models were conducted to ensure that we weren't going too heavy on certain aspects of the building. So they settled on an R30 roof, R19 insulation, which was actually reused, and they only used the clean stuff, obviously not the dirty stuff, from the building when it was sitting. High performance glazing, a 0.3 U value on the windows, which is great. So a heat gain coefficient of about 0.28. Great window system. They added clear story windows, skylights, and solar tubes to really open the building up. There's actually 3 solar tubes right behind you, very bright. They did, on the lighting side, motion sensing task lighting, multi-zonal control of the main office area, which was programmed accordingly based on operating hours, with overrides obviously, and daylight sensors tied to lighting controls. More importantly, the whole reason I'm here is to discuss how this building uses geothermal. Though it is a supply system, it is still a heat pump system. You might ask, well, if we have 160 degrees, why don't we use it directly in the floor? There are zones where Russ did design that in, where we're using that directly. However, using heat pumps on what's called a source loop allows for a certain bit of redundancy. So if, God forbid, the supply line gets colder than 160 or goes out for a day or two, we're not completely sunk. We can still heat the building accordingly. So it's not that we couldn't, or Russ couldn't have used it. They just use it as that redundancy point. So there's a schematic on the next page. However, the way that the HVAC system works is this concept of a source loop. So there's literally a hot water loop that goes around this building, which is kept at about 70 degrees. It's variable. We found that we didn't want to just keep it at 70 degrees for a reason. I'll get into that in the next slide. We keep that at, by heating. Addition water is the heat addition water is the city geothermal system. Heat rejection on that source loop is the cooling tower. As heat pumps turn on and off, they're either going to add or subtract heat from the loop. Those two source loop pieces of equipment are there to recover it, however way it needs to have it. There's a combination of water source heat pumps here, both water to water, water to air. The entire radiant floor, which is out in that big office area, are run off the water to water heat pumps. The water to water heat pumps, which on the other side of the heat pump, not the side that's connected to the source loop, run about 105-degree water through this floor accordingly. The floor is insulated, kind of looks like Legos, but it's about 3 inches of insulation that sits below, so we're not losing heat down. Even though heat rises, we're still insulating it. There's literally miles and miles of this piping in that space over there. Russ has all the information on exactly how many miles, but it's quite a bit. We also use water to air heat pumps, which this a system in here is a water to air heat pump. The idea between a water source, or the idea behind a water source heat pump, is that we don't stick our condenser up on the roof or outside and subject our refrigeration cycle to outside air conditions. By having this source loop available, the heat pump is allowed to operate consistently throughout the year at its peak efficiency and capacity. So if it's 0 degrees out, your water to air heat pump or your air to air heat pump, which is the traditional heat pump, actually loses capacity exponentially after 30 degrees. We don't lose any capacity this way. So the building is completely, the HVAC system is not relying on the outdoor air whatsoever. Discuss the radiant floor and air side systems. We also have energy recovery on the bathroom. We won't get into that right now. If you have questions after, you can ask me about how we do that. And a CPU exhaust system. Domestic hot water is 100% geothermal, so we bring that 160-degree water in and heat the domestic water. This is the schematic. Very complex. This is the brainchild of Russ. I want to pay attention to this side, which is our connection to the geothermal loop. So these two pipes right here come in from the geothermal. There's one pump which circulates through a water-to-water heat exchanger. The other side of the water-to-water heat exchanger, which is this side, goes out to the building, and it's based on a control valve operation, so it tempers the source loop accordingly. Keeps it at 70 degrees, even though we start losing it as certain zones go into heating. You'll notice that all of the water-to-water heat pumps, all of the water-to-air heat pumps are somehow connected to this. This is the domestic hot water heater. You'll notice, again, direct use. This goes, obviously heats the water, so that's the direct use. Also notice there are a couple other direct uses of the source loop, which are, these are exterior zones. These are the radiant manifolds that you'll see out there if you've taken a tour of the building. These radiant manifolds on the exterior of the building actually operate at that 160-degree water when there's a call. So if it's 0 degrees out, the idea behind that is, well, let's stop the heat before it gets too far in so that the water-to-water heat pump can do its job efficiently while still keeping the building comfortable. So 0 degrees out, that zone, which is literally a strip this wide of geothermal line, turns on, heats up that zone to wash the walls, both the north and south side. Fin tube radiator in the garbage room, another direct use, and then the ERV has its own coil.
Mike, do they do multiple strategies just to test out different options, or?
Say that again, I'm sorry?
You guys were talking about different systems in different parts of the building. Is that just so they could test different strategies, or?
That was part of it, yeah. They wanted to see what was going to work best for their clients in the future. But yet it's still an integrated system, so it's not like, okay, we need to shut down one, do the other. It all operates together. I think they're most happiest with the water-to-water heat pumps, especially if there's going to be more collection buildings coming online. I think they were pretty happy with that. So, the use of geothermal, as I said, fin tube radiator, exterior zones, coil in the ERV, all direct uses. You can call source loop heat addition a direct use, right? Because we're heating up a source loop independently of the source loop operating on its own. Those are direct uses. Heat addition, the city geothermal comes in at 160 degrees, as John indicated. I found little to no variance in that 160 degrees, by the way. It stayed pretty constant throughout the year. The source loop temperature optimized for heat pump operation. Okay, so that's what I was kind of talking or alluding to in the previous slides. These are graphs of wattage of the heat pumps themselves versus source loop temperature. which would have a direct impact on how we use geothermal or the cooling tower up on the roof. As you can see, even the water-to-air heat pumps, even though they're incredibly efficient on both ends of the spectrum, still can get even more efficient depending on where you keep the source loop temperature. So during the summer, when we're trying to reject a bunch of heat of the building itself, we actually run as cold temperature as we can on that source loop, which actually ends up being a little bit below 69 at times. It depends on another efficiency point, which has nothing to do with this conversation, but the cooling tower itself has its sweet spot as well. So that was an optimization there that we found. But on the heating side, there's much, the slope of the line's not as aggressive as on the cooling side of the heat pump. So we found we could probably keep this thing at 80 degrees, even though I think design said keep it at 70, and have a somewhat decent wattage, not really gaining much if we go all the way up to 95, which would then max out maybe what we needed to use on the geothermal side of things. So we decided on somewhere between 85 and 90 degrees to keep that source loop in the winter. In the spring and the fall, the shoulder periods, different story. So I won't get into that now. The controls were altered during commissioning to maximize the source loop delta T to minimize the quantity, because as John said, we're billed by the gallon here. So we had delta T's up to 70 degrees at times. That was actually pretty consistent throughout the year. We had that 70 degree, and this is on the city side. So they're pumping in the 160. We're slowing that temperature down on the other side of the heat exchanger, the load loop side of the heat exchanger, so that we can get 70, in some cases up to 80 and 90 degrees. This is just a typical figure. There are times when it gets down to 50, which is, we obviously don't want to go below that. That's when we start losing our cost effectiveness. And again, domestic hot water, direct use of city geothermal. How does the building compare? This is very brief. You're probably going to notice, at least Tanya noticed on the spreadsheet. Why is this one so high in October? You remember why that happened? There was a valving issue. When you try to have, on this side, not your side, when you try to do too many things with the geothermal, you need, as engineers, we size valves for the worst case scenario, right? Well, this is what happens in worst case scenario with a valve that's sized that accordingly, right? We open a valve for design day when it's fallout. Well, that valve lets all kinds of water come in. So anyway, during commissioning, I worked with both Russ and the controls contractor to figure out a better valving technique. And as you can see, we're down, and even a year later, this is year 2. That's the comparison there. It's a staged valve, so we still have the max valve for design day, but we have a much smaller valve which lets just a little bit of water in if we need to, specifically for domestic water. Electricity usage also went down, not really very important for the geothermal discussion right now. Sorry, Tanya. Electricity, and this is proven. Over the last 2 years I've been tracking the bills. Is everyone familiar with Energy Use Index, EUI? It's a metric used to compare a building. It's an energy density per square foot. On the electricity side, we were kind of bottoming out at about 25.1 kilobtu's per square foot per year. On the geothermal, using the 50 degree delta, we're at 8.8 on the EUI side. It's incredibly low, especially if you compare that to the average office building in Idaho, which is 89. These are some other source EUIs. It doesn't directly translate because source is different from site, but those figures over there are all site. And it shows that some kind of innovative design will get you below what the VRF systems, the dedicated outdoor air systems, other systems that were deemed as energy efficient will get you if you kind of take that extra step in design. Banner Bank, Boise is operating at 37. However, I believe that's a conceptual number. I don't know if it's actually operating at that. Anyway, just for comparison's sake. So 33.9, a great figure, which was probably within a couple percentage points of what the energy modeling was saying. So that's kind of where we wanted to stop was at that point. We figured commissioning was over at that point. So again, Mike Jones, all the relevant people that you might want to talk to about this building is there. Obviously, this building uses geothermal, so thanks for your time.
So I'm sorry to rush Mike, but great job to both of our presenters for getting all that content out. If you want to, reply after, does anybody have any questions they want to shoot at Mike right now after that fast presentation? Okay.
Are you guys gonna stick around and chat with people afterwards if they want to? Okay.
Does anybody have any questions about Concordia's connection specifically, or is this another neighborhood connection, recent connection? Okay, so if anybody has follow-up questions, you think of something, just contact me and I can connect you together. And definitely appreciate you all coming out. If you have an interest in electric vehicles and electric vehicle charging stations, the Boise State University Environmental Studies students have done a great report. I've got the executive summary sitting right there. If that piques your interest, contact me and I'll send you the full report. But what I did was take a look at downtown Boise and compare it to national drivers for electric vehicle charging stations and where would be a good opportunity to place them in downtown Boise. So thanks very much for your time, and we'll see you at the next one.
Are you guys working on it? Really? That should be interesting. In terms of the cost of it.
Oh, on Mike's. Yeah, I'm gonna chat with you guys for a little bit before I go back. Oh, yeah, are you leaving? So, yeah, you can. Maybe they're just waiting to see how it's Cool. Yeah, look forward to
Yeah, no, this will be good. It's might be a little.
Learn more about us, about the whole process. Might be a little.
They're in their. I imagine.
Yeah, and you see the ideal as well. Hi, Selena.
No, you know, they wrote back those grants. Probably they're just looking at it. Yeah, those are solar turbines. Yeah, pretty bright. You know, here, in these 3 years, that.
I've been emailing them back and forth.